How does imagination develop? Learning outcomes. After reading this chapter, you will be able to describe the development of imagination, creativity, and flexible thinking. Understand how children express their creativity in their drawings, their imaginary worlds, and in what they are willing to believe. Provide examples of how children imagination is grounded in their everyday experience. Introduction. Humans are often celebrated by humans, it has to be said, as the most inventive and creative of species. Chimpanzees can use stones to crush nuts. Some crows use sticks to catch grubs. An octopus have been known to use coconut shells to disguise themselves from predators. Impressive as these behaviours are, they do not really compare with the depth and breadth of human innovation. Clothes, sanitation, levers, the wheel, the plough, music, paper, ice, architecture, clocks, the compass, currency, refrigeration, vaccines, birth control, gene editing, computers, the internet, and artificial intelligence. Where most other animals adapt to their environment, we adapt to the environment to us. We don't wait around to evolve thicker hair, we invent the coat. This adaptability has allowed us to inhabit every continent and make an impact on the Earth's entire ecosystem. Not in a positive way. We are good at innovation and we value it too. Creativity is one of the most desired employability skills. Creative industries are major revenue sources for larger economies, and highly skilled artists, musicians, dancers, storytellers, and other creators are among the most idolized members of many societies. The human capacities for technological innovation and creative problem solving far surpass those of any species, and significantly develop during middle childhood. How do children use their imagination? Are children able to innovate new tools, imagine impossible worlds, and suspend reality? How do they make judgments about what is possible? And what can we learn from children's figurative drawing, their pretend play, and their imaginary companions? Tool innovation. One way to measure children's inventiveness is putting them in a situation that demands creative thinking. For example, in one popular problem-solving task, children are presented with a transparent tube with a small bucket at the bottom. Inside the bucket is a reward, typically a sticker or a sweet, and alongside the tube is a straightened pipe cleaner. The tube is too long and too narrow for the children to simply reach down and grab the reward, so they must find another way to retrieve it. To do so, the children need to bend the pipe cleaner into a hook shape and use that to pull the bucket up out of the tube. When researchers gave this task to children of different ages, they were surprised by just how challenging even the older ones found it. Fewer than 1 in 10 children under 5 years of age made a hook. Only about half of 7 to 8 year olds were successful in fishing the bucket from the tube, and almost a third of 11-year-olds failed entirely. Beck et al. 2011. However, when Betty the Crow was given an equivalent task, she succeeded without a problem. Weir et al. 2002. Crows come from a family of birds called corvids, which are known for their intelligence. Corvids have a much longer period of immaturity compared with birds like chickens, geese and turkeys. Chickens grow up being good for a few things, like pecking, but corvids grow to be more adaptable and able to generalize their skills. It is no coincidence that corvids have a relatively long early learning phase of life, play more as juveniles, and have patient adult teachers. The behaviour of the children we looked at in section 1 revealed remarkable sophistication at even young ages in the terms of reading others' minds, chapter 3, learning languages, chapter 4, and inferring cause and effect, chapter 5. But the tool innovation, they are remarkable for the opposite reason. Despite being prodigious in all these other areas, it is surprising just how difficult children find an apparently straightforward task involving just a bucket and a pipe cleaner. Even 11-year-olds are outsmarted by a crow when what is going on here. First, children's poor performance at the task is not due to difficulty in forming a hook with a pipe cleaner, as they have similar problems in creating a loop to access an out-of-reach platform, pouring water into a tube to bring a toy into reach, or unbending pipe cleaners to push a ball from a horizontal tube. It is also not something particular to weird children, as this basic finding has been widely replicated across diverse cultures in over a dozen different countries. For example, Nielsen and colleagues 2014 compared the performance of most middle-class 3 to 5-year-old children from Brisbane with children from 5 South African communities, in which children typically lack access to manufactured toys and so make their own. We might expect that experience with regularly making toys would make the San children more likely to innovate a solution to this task. However, only 11% of Brisbane children and no San children formed a hook in the task. And it's not the children's lack of physical tool-making abilities to make a hook either. When children watch an adult bend a pipe cleaner into a hook to retrieve the reward, they can copy them without a problem. Perhaps children lack experience with pipe cleaners or fail to understand that they are free to make whatever they like with them. When children are encouraged to experiment with what pipe cleaners can do by twisting them around a pen, for example, this doesn't seem to put 4 to 7-year-olds at significant advantage. When later confronted with a hook task, cutting a towel 2011, and when children are clearly given license by a puppet to make something new, Hines says he has some things here you can make something with to get the sticker. The clear innovation to innovate has little impact on success in the task either in 9.1. Examples of tools used in crows, monkeys, octopus and children in chapter 1 were mentioned that scientists are obsessed with arguing over alternative explanations to explain the same set of observations because they care about cause and effect. The hook task is a good example of the debate in action, as researchers have explained several plausible explanations for the observed results, ruling each one out in turn. There are likely to be a range of factors that make the hook task difficult for children, Rawling 2022. While on the surface the solution seems straightforward to us, it places significant demands on children's imagination, memory, planning, flexible thinking skills. For example, children need to hold the current state of the task in their mind. The reward is at the bottom of the tube, while also remembering what they are trying to achieve. Get the reward out of the tube, at the same time as visualizing a solution, a hook, and planning the sequence of actions to get from the current state to where they want to be. This demands high-level thinking skills that are some of the last to mature in development. We revisit these so-called executive function skills in section 3, in support of the idea that these skills matter as planning and control abilities develop. Children's success on the hook task also gets better. Another barrier to success is that children can get fixated on conventional use of a tool and find it difficult to imagine using it in a way that is different from how it was originally intended. For example, 12 to 18 months old finds it difficult to use the handle end of a spoon to illuminate a light box. But when a tool is introduced to them that they have seen before, they show more willingness to use it in a different ways. Barrett et al. 2007. Presumably, in their everyday experience, these infants have been many instances of spoon use before, and therefore had a strong expectations about how a spoon should be used. We know infants are prodigious imitators of adults' behaviour. Recall infants imitating adults touching a light-up box with their head in chapter 5. Without such faithful imitation, most of our cultural knowledge would be lost from one generation to the next. But in the case of innovation, the preference to copy what has gone before gets in the way of thinking differently. And thinking differently is exactly what is needed in these types of tasks. We will see later in chapter 12 how teenagers healthily disregard for tradition. There must be a better way, and openness to new experiences can put them at an advantage when it comes to innovating and leading cultural changes. Researchers have had success in boosting young children's performance on the hook task if they are allowed to tinker with the past inventions. Burdett and Ronford, 2023. Those children who retained tools from earlier failed attempts and who added more novel objects to their tools following failure were more likely to build successful tools later. This is reminiscent of the ratchet effect we met in chapter 5, whereby we take the discoveries, behaviours and innovations of previous generations and build on them for future ones. But instead of ratcheting better ideas over generations, children are ratcheting better ideas from their previous selves, tinkering their way to a solution. Key points. Tool innovation emerges relatively late in childhood compared to other complex skills. Tool innovation places significant demands on higher order thinking skills and is hindered by a performance to imitate the conventional use of an object. Children show signs of greater inventiveness as they get older and get better at identifying a workable solution among a range of possibilities. How does imagination develop? Learning outcomes. After reading this chapter, you will be able to describe the development of imagination, creativity, and flexible thinking. Understand how children express their creativity in their drawings, their imaginary worlds, and in what